VR telepresence is the practice of using a drone, robot, or other mobile system to project a 360-degree environment into a user's VR headset, allowing that user to functionally explore the robot's environment through the headset. This kind of technology has a wide range of applications, including remote work, telemedicine, virtual tourism, or even running inspections in unsafe areas. The idea of VR telepresence is far from new. Some projects dating back to the late 90s explore the idea of projecting a stereographic camera view from an RC car or similar mobile system. These cars are typically piloted with a standard joystick controller. These days, VR technology has expanded exponentially, but the control theory behind exploring with these robots is largely the same. These robots have remained non-holonomic cars that are controlled by joysticks or keyboards. Not only is this not very immersive, but having the environment move while you stay still can easily cause motion sickness. Our goal with this project was to leverage current VR technology to make a more immersive exploration experience for the user. Modern headsets use a variety of IMUs and cameras to capture the user's XYZ position in space, which we can use to give movement instructions to our robot. This means that the user can explore the virtual environment by physically walking around, bending over, and using other physical movements. By the end of the year, we were able to design and implement a fast, responsive robotic system that communicates with the MetaQuest headset to follow the user's motion and generate a remote environment for the user to explore in real time. This project has three main subsystems: the VR headset, the data intermediary, which hosts the servers that information is passed through, and the mobile robot itself. The VR headset passes its XYZ position up as an MQTT message, where the robot catches it and moves to that position with its lateral locomotion system and vertical actuator. While this happens, the 360-degree video on top of the vertical lift is passed along via an HTTP server. Because of how we interface with the camera, the headset receives the video footage as two flat rectangles, one for each lens. The software on the headset, which is a Unity project file, works to automatically warp that image into a spherical environment around the user. This environment updates around 30 frames per second to give the users an up-to-date view of the robot's perspective. Meanwhile, the robot has three subsystems that contribute to its motion. The robot control subsystem, which is mainly the Raspberry Pi, handles video and position communication with the headset. It also distributes the headset's movement goals to the other subsystems. The vertical actuator is responsible for the Z-coordinate goal. This is a 3 foot to 6.5 foot high rack and pinion system, with a 360-degree camera mounted on top to match the user's eye level. And finally, the XY movement is mapped to 4 smart motor controllers in the locomotion subsystem. These are individual modules with microcontrollers that oversee PID trajectories for each wheel in a holonomic X-drive configuration. With all of these systems and subsystems working together, we get our operational VR telepresence robot. Thank you so much for watching. We'd like to especially thank Professor Rosendo and Professor Murai for being our advisors on this project.